I'd like to finish our discussion of Riemann sums by talking about other Riemann sums. And so far, we've talked about 4 named approximations. We've looked at the left-hand sum, the right-hand sum, midpoint sum, and the trapezoid rule. So we're going back to our general context. I'm approximating the area under f of x over the interval from a to b using n rectangles. And I've boxed in red important notation in the way in which we've defined that earlier, as we are going to continue to use that. So it's important that you have those equations in mind. So what I wanted to point out so far is the way that we chose the height in our kth interval was really what was affected by the different sums we looked at. For instance, in the interval from xk minus 1 to xk, if we chose the height to be f of xk minus 1, that was the left-hand sum. If we chose the height to be f of xk, then that was the right-hand sum, and so on. But what I want to point out is that we can choose the height of our kth rectangle to be f of x, where x could be any point in the kth subinterval. And what I really want to emphasize here is any point. So what I'm saying here is you could have infinitely many different Riemann sums. Of course, we're not going to name more than what we've looked at so far, but I do want to just point out that there are so many choices for what we could use as the height. So thinking about the general way I could write then a Riemann sum is that we can express our Riemann sum as f of x1 star times delta x plus f of x2 star times delta x all the way through f of xn star delta x, which we can put in sigma notation as the sum from k equals 1 to n of f of x k star times delta x. So this notation is often confusing the first time we see it. In particular, what do we mean by the star notation? So when I'm writing out this sum, I'm not specifying exactly what xk star is. So in general, all I'm claiming is that xk star is some point in the interval xk minus 1 to xk. And importantly, that is a closed interval. We're including those endpoints. So the choices of the xk star, those do not have to follow any pattern, and the distances between consecutive xk star values could vary. I'm not claiming that the rectangles have varying widths, but just the location of where I'm choosing my x value within those subintervals can vary. So I expect that might still be confusing. We are going to finish up with an example where I can come back to that and hopefully clear that up in case that is unclear. What I want to point out, though, is in terms of this choice, in what we've seen so far, when we're looking at LHS, that implies that we choose xk star always to equal the leftmost point in our subinterval. That's the particular way I take my general Riemann sum form and make it into left-hand sum. If I have the right-hand sum, what that is implying is that I'm choosing always xk star to equal xk, the rightmost point of my interval. And in the midpoint sum, I'm making the choice that for each subinterval, the value of x I'm plugging into the function in order to find the height, is xk minus 1 plus xk all over 2, or exactly the midpoint there. And again, these are just 3 examples of Riemann sums in terms of how I'm choosing xk star, and there are infinitely many such choices. So one nice kind of choice is a maximum Riemann sum or a minimum Riemann sum. And instead of giving that any kind of formal definition, I'd like to jump right into an example and we can look at that. So the example I'm going to look at here is, so let's see, f of x is cosine x plus 2. And we're looking in particular at the interval from minus pi over 2 to 3 pi over 2. So if you're drawing this, think about drawing just the regular cosine function, but I've shifted it up by 2. So we have this picture here. I guess I should point out that when I graphed this is a little bit misleading. Shifting that up by 2, this is not y equals 0. And in hindsight, I wish I'd fixed that. So notice that this kind of is 1. So I made this a while ago on Maple, and it seemed to have condensed that axis. That's okay. We can still get across what I want to look at here. So I'm going to come back to that picture in a moment. So let's label this maximum and minimum Riemann sums. So we've got our function. What I would like to do with that picture, and maybe to avoid confusion, I'll just kind of sketch it here. So what I want to do here is find the maximum Riemann sum using 3 rectangles. So a couple things. I'm saying find the maximum Riemann sum possible to estimate the area under this curve on this interval. And one thing we'll also see is that whenever I talk about the maximum Riemann sum, it's very much going to depend on the number of rectangles. So I'm specifying 3, and we want to find the maximum Riemann sum. So what that's saying is, given that we choose 3 rectangles of equal width, how can we select the heights so that we get the largest possible area when we're adding up our 3 rectangles? So a couple things. As soon as we say 3 rectangles, what we know is that delta x is going to be, right, it's b minus a over n. So it's going to be 3 pi over 2 minus negative pi over 2 divided by our n equals 3. So we get 4 pi over 6, actually, or 2 pi over 3. So that's delta x. So if I start to think about what my xk's would be, we can compute that. Remember that xk is a plus k delta x. A here is minus pi over 2. And we just computed delta x. And we could make that maybe even simpler if we got a common denominator, that we're going to have negative 3 pi over 6 plus 4 pi over 6 times k. So what I get out of this is x sub 0 is negative pi over 2. I'm going to add to that 4 pi over 6, and that's going to leave me with 1 pi over 6. x2 is going to be 5 pi over 6, and then finally x3 is the last point in our interval, 3 pi over 2. So those are my values. And what I want to think about here is my picture. which, like I said, I want to resketch. So we saw that it pretty much looked like this, where, let's see, this min value should have been 1, and this max value should have been 3, because we're shifting cosine up by 2. So in terms of looking at this picture, this is minus pi over 2, and this is going to be positive 3 pi over 2. This would be 0. And so if I start to think about putting this into, just to point out, this is going to be 0. Maybe I should not put this here, but that's where the axes would be. When I want to put my rectangles in there, now I know kind of where the cutoffs are. So I'm going to look at about pi over 6. That would be maybe about here. We're going to have 5 pi over 6. And so when we look at that, that's going to be roughly, so this would be maybe about here. This is not perfect, but something like this. And those should be a little bit more equally represented, but these are my cutoffs. So this is 5 pi over 6, and I'm going to delete that. So what we get to do is choose the height. What I'm going to do here is, let's use red. What I'm going to look at, and of course if I have a graph, what I can do is take advantage of looking at that graph. So in this very first picture, I want to choose the largest possible y value I can. And notice the maximum value of the function actually occurs right here. It happens at 0. And so that is going to be what I want to select for my first rectangle. A couple things I want to point out here. Notice that that's not the right point, the left point, the midpoint. It's just somewhere in there. And in fact, I didn't focus on where it occurred too much on the x-axis. It just happened to be the largest possible y value. When I move to my next rectangle, then what is standing out to me that on this subinterval, the function is strictly decreasing. So I can see that the largest possible y value is going to come from choosing a left-hand rectangle. And on the last one, it starts by decreasing and then it continues to increase. So that would mean that the largest height would have to occur at one of the two sides. It happens, we can see at the right point here. And so in terms of my maximum Riemann sum, the red rectangles here are the largest possible rectangles of equal width that I could choose to give me that. And so a couple points to see here, in terms of my choices, x1 star, so the x value that was used to find the height in the first rectangle, that was 0. Oops. And f of x1 star is then f of 0, which is 3. x2 star, if you remember, we chose the leftmost point, which was pi over 6. Oops, pi over 6. So f of x2 star was f of pi over 6. And that would yield 2 plus root 3 over 2. And then finally, x3 star, we chose the rightmost point. So in this case, 3 pi over 2. So in plugging that in to find the height of that rectangle, we are going to end up with 2. So I want to come back to a point that I said I was hoping to clear up. Notice what I meant when I was saying that the distance between consecutive xk stars can vary. That means that from x1 star to x2 star, we took a jump of pi over 6. But then notice that we took a much larger jump in moving from x2 star to x3 star. So that's what I meant before. But we still had a fixed delta x and a common width for those 3 rectangles. But the location where we were choosing the height, that's what I was talking about varying there. So in terms of finding my maximum Riemann sum in this case, now we have everything we need. And it's going to be equal to our heights, so 3 plus 2 plus root 3 over 2 plus 2. And they have a common width of 2 pi over 3. And so putting that all together, it doesn't simplify terribly nicely, but we get our maximum Riemann sum. So if you were going to choose 3 rectangles and choose the heights for those, you could never come up with a larger number for the sum of the areas of those 3 rectangles. And that's what we mean by the maximum Riemann sum. Now, as you might guess, I could go back and do the same thing for the minimum Riemann sum. I'll use blue here on that same picture. This work that I did before in finding delta x and xk, that all stays the same. So I get to take advantage of that. So in some sense now, when I'm thinking about the edges of my rectangles, those are the same. But I want to now consider the opposite question. Where's the smallest possible height I could choose? So in this first rectangle, notice that the function is increasing and then decreasing. So in that instance, the minimum would have to be at one of the 2 edges. I can see that it appears to be on the left edge. So I'm going to choose my first rectangle to be this one. In my second subinterval, the function is strictly decreasing. So the smallest possible y value is choosing the rightmost point there. And then the minimum of the function actually occurs in this last rectangle. And again, I know that from my shape of cosine in general. And so that's going to occur at pi. And that's going to be roughly here. And so that's going to be the smallest possible height I could choose. Again, my scheme in making that choice was very different for each of the 3 rectangles. So if we think about the minimum, I've illustrated it up there, but I'll point out that x1 star in the minimum case ended up being the choice of the leftmost point minus pi over 2. So in finding that height, we plug in minus pi over 2, and that gives us the value of 2. x2 star, we ended up choosing the rightmost point at 5 pi over 6. And that's going to yield 2 minus root 3 over 2. And finally, x3 star, we chose the minimum value of the function, which occurred at pi. Whoops. So this is x3 star, and this is f of pi, and that would give us the value of 1. So in wrapping this up, finding the min Riemann sum in this instance, again, assuming 3 rectangles of equal width, we see that we're going to get the sum of these heights. Again, I want to multiply that by that common width of 2 pi over 3. And we get 5 minus root 3 over 2, all multiplied by 2 pi over 3. And again, in finding a Riemann sum with 3 rectangles of equal width for this scenario, we would never be able to find a smaller outcome in terms of the total sum of those areas.